Hello there, and welcome to Earth's History, where we examine the rhythms that govern our planet's climate, where we explore the mysterious cycles that have transformed Earth from ice-covered wasteland to temperate paradise, and back again dozens of times across the past few million years, where we ask why our planet experiences regular, predictable ice ages approximately every 100,000 years. Glacial periods, when ice sheets kilometers thick spread across continents, sea levels drop by over 100 meters, global temperatures plunge, and Earth becomes nearly unrecognizable compared to the warm interglacial periods between the freezes, and where we contemplate the unsettling reality that we are currently living in one of those brief warm intervals, a temporary respite that has lasted about 11,700 years and might be approaching its end, with the next ice age potentially beginning within the next few thousand years, unless human activities have disrupted the cycle in ways we don't fully understand. If you've ever wondered why ice ages occur with such regularity, if you've questioned what causes a planet to periodically plunge into deep freeze, if you've contemplated the massive ice sheets that once covered regions where millions of people now live, if you've thought about the fact that for 90% of the past million years, Earth has been colder than today, much colder, with ice sheets extending from the poles nearly to the equator, with forests replaced by tundra, with coastlines hundreds of kilometers farther out than today's because so much water was locked in ice, you're beginning to touch on one of climate science's most important and fascinating questions. What drives the 100,000-year cycle of ice ages, and what does understanding this cycle mean for our species, which evolved during these extreme climate oscillations and now faces a future where our own activities might be overriding natural cycles in unpredictable ways? Wherever you are right now, I hope you're comfortable, settled, ready to journey through climate history spanning millions of years, to explore the astronomical forces that govern Earth's relationship with the Sun, to understand the feedback mechanisms that amplify small changes into massive ice sheets, and to contemplate that the climate we consider normal, the warm, stable Holocene epoch of the past 11,700 years that allowed agriculture, civilization, and everything we call human progress to develop, is actually abnormal, a brief interglacial pause in a planet whose dominant state for the past million years has been Ice Age, and which will almost certainly return to that dominant state eventually, unless we've fundamentally altered the system in ways that prevent the next freeze. If this exploration into Earth's Ice Age cycles changes how you see climate, if it makes you appreciate the delicate balance that keeps our planet habitable, if it inspires you to support climate science and policy that accounts for both natural cycles and human impacts, if it helps you understand that climate has never been stable, but has oscillated wildly throughout Earth's history, making our current warm period precious and temporary, I'd be grateful if you'd like the video, subscribe to the channel, or share it with someone else who understands that knowing why Earth freezes regularly is essential for understanding where we are in the cycle, where we're heading, and how our actions might affect what comes next. So settle in. Let your breathing synchronize with the slow advance and retreat of glaciers, each breath like 1,000 years, each exhalation like 10,000 winters compressed into a moment. Let your mind expand to hold timescales where human lifetimes disappear into statistical irrelevance, and where the rise and fall of entire civilizations occurs within the warm intervals between the ice. Let yourself feel the cold of glacial periods when ice sheets thousands of meters thick buried the landscapes you know, when global temperatures were 5 to 8 degrees colder than today, when humanity's ancestors huddled in refugia near the equator or on ice-free coastlines, surviving but barely, waiting for the warmth that would eventually return as it always does, until the cycle turns again and the ice returns as it always does. And let's begin our investigation into why Earth suddenly freezes every 100,000 years, examining the astronomical mechanics, the climate feedbacks, the geological evidence, and what this cyclical freezing means for understanding our current climate, our recent past, and our uncertain future, on a planet that has spent most of its recent history locked in ice. The Ice Age cycle, pattern recognition. To understand why Earth freezes every 100,000 years, we must first establish that this pattern exists and define what we mean by Ice Age. Terminology clarification: Ice Age, capital E, capital A, the broader period during which Earth experiences repeated glacial interglacial cycles. We're currently in an ice age that began approximately 2.6 million years ago, the Quaternary glaciation, and continues today. Glacial period, or glaciation. Cold phases within the ice age when ice sheets expand, covering vast areas of continents. These are the ice ages, lowercase in popular usage. Interglacial period. Warm phases within the ice age when ice sheets retreat to polar regions. We currently live in an interglacial called the Holocene. The pattern we're examining. During the current ice age, past 2.6 million years, Earth has experienced cycles of glacial and interglacial periods with striking regularity, particularly over the past million years, when the dominant cycle has been approximately 100,000 years. Observing the cycle. How we know about past climate. Scientists reconstruct past temperatures and ice volumes through multiple proxy methods. Ice cores. Drilling into Antarctic and Greenland ice sheets retrieves cores containing ice up to 800,000 years old. Epica ice core in Antarctica. Air bubbles trapped in the ice preserve atmospheric composition, CO2, methane, etc., from when the snow fell. Oxygen isotope ratios in the ice indicate temperature. Ocean sediment cores. Drilling into ocean floor sediments retrieves cores going back millions of years. Oxygen isotope ratios in fossilized shells, foraminifera, indicate ice volume and ocean temperature. Higher D18O, oxygen 18 ratios indicate more ice on land, because water containing lighter, oxygen 16, preferentially evaporates and gets locked in ice sheets, leaving oceans enriched in heavier oxygen 18. Other proxies, pollen records, indicating vegetation and thus climate, cave formations, stalactites, stalagmites, coral growth rings, tree rings for more recent periods, glacial deposits and moraines, showing ice sheet extent. The data reveal a striking pattern. 100,000-year cycle dominance, past a million years. Over the past million years, the primary climate cycle has been approximately 100,000 years. 90,000 years of gradual cooling and ice sheet growth, glacial inception and expansion. 10,000 years of relatively warm interglacial period, rapid transition, 10,000 years, from interglacial back to glacial conditions, extremely rapid termination, 5,000 years or less, from full glacial to interglacial. The cycle is asymmetric, long, slow cooling followed by rapid warming, called sawtooth pattern in graphs. 41,000-year cycle dominance, 2.6 to 1 million years ago. Before about 1 million years ago, but after 2.6 million years ago, the dominant cycle was approximately 41,000 years. Glacial interglacial cycles occurred more frequently and were less extreme. The mid-Pleistocene transition, MPT. Around 1.2 Justus or 8 million years ago, Earth's climate system underwent a transition. Cycle period doubled from 41,000 to 100,000 years. Glacial periods became more intense. Ice sheets grew larger. Temperature oscillations increased in amplitude. Why this transition occurred is one of climate science's major mysteries. We'll explore it later, but it's important to note that the 100,000-year cycle is relatively recent in Earth's history, a phenomenon of the past million years, not characteristic of earlier ice ages or most of Earth's history. Recent glacial interglacial cycles. Let's examine the past several cycles to see the pattern clearly. Marine isotope stage 1, MIS1, present interglacial, Holocene. Began 11,700 years ago. Current warm period. Relatively stable temperatures. Human civilization developed entirely during this interglacial MIS2, last glacial maximum LGM. Peak glaciation. 26,000–19,000 years ago. Ice sheets covered. Northern Europe, Fennoscandia. Most of Britain, Canada and northern USA, Laurentide ice sheet. Northern Asia, global temperature, 80 or colder than present sea level. 120–130 meters lower than present. Ended with rapid warming, 19,000, 11,700 years ago. Termination of solaire, -3–4. Moderate glacial conditions, just in 60,000, 30,000 years. Egger ice sheets present but not at maximum extent. Fluctuating conditions, MIS FAMVE. Eemian interglacial, 130,000, 115,000 years ago. Previous interglacial period, temperatures possibly 1 to pre-eons or warmer than present sea levels forced to 6 meters higher than present, less ice than today, ended with return to glacial conditions, MISCE6. Penultimate glaciation. 190,000, 130,000 years ago, major glaciation before the Eemian. This pattern repeats, approximately 100,000 year cycles of long glacial periods interrupted by brief 10,000, 20,000 year warm interglacials. Key observations. 1. Regularity. The cycle repeats with remarkable consistency over the past million years. 2. Asymmetry. Slow cooling into glaciation, tens of thousands of years. Rapid warming out of glaciation, thousands of years. 3. Threshold behavior. Glacial inception and termination seem to involve threshold crossings, gradual changes until a tipping point, then rapid transition. 4. Global coordination. Climate changes occur globally, though with regional variations and time lags. When Northern Hemisphere enters glaciation, Southern Hemisphere also cools, though patterns differ due to hemispheric differences in land distribution. 5. Current position in cycle. We're about 11,700 years into the current interglacial. Based on previous cycles, natural progression would suggest we're approaching the end of the interglacial and should be entering the next glaciation within the next few thousand years, except human greenhouse gas emissions might have delayed or prevented this. The fundamental question: what causes this 100,000-year cycle? Why does Earth's climate oscillate so regularly? The answer involves astronomy, orbital mechanics, solar energy distribution, and Earth's internal feedback mechanisms working together in a complex system that scientists are still working to fully understand. The Milankovitch cycles, astronomical pacemakers. The Serbian scientist Milutin Milanković, 1879–1958, proposed in the early 20th century that ice ages are caused by variations in Earth's orbit around the Sun and the orientation of Earth's axis, which affect the amount and distribution of solar energy reaching Earth's surface. These orbital variations, now called Milankovitch cycles, operate on timescales of tens to hundreds of thousands of years and are now recognized as the primary pacemakers of ice age cycles. 3 main orbital parameters vary cyclically. 1. Eccentricity, orbital shape. Earth's orbit around the Sun is not perfectly circular. It's an ellipse with the Sun at one focus. The degree of ellipticity, how stretched out the ellipse is, varies cyclically. Current eccentricity, 0,167, nearly circular. 0,2, perfect circle. 1,0, straight line. Eccentricity range varies between Kassus, nearly circular, and Gelsus-Pintosus, more elliptical. Cycle periods: primary cycle, 100,000 years. Secondary cycle, from 213,000 years. Effect on climate. When eccentricity is high, more elliptical orbit, Earth's distance from Sun varies more between perihelion, closest approach, and aphelion, farthest point. Currently, Earth is 147 million kilometers from Sun at perihelion, early January, and 152 million kilometers at aphelion, early July. This 3% difference in distance creates a 6% difference in solar energy received. When eccentricity is low, nearly circular orbit, distance variation is minimal. Solar energy received varies little between perihelion and aphelion. Key point: eccentricity affects total annual solar energy received by Earth. Higher eccentricity means greater seasonal contrast. One hemisphere's summer much warmer, winter much colder, depending on when perihelion occurs. Current situation: eccentricity is relatively low and decreasing, meaning orbit is becoming more circular. This reduces seasonal contrast. 2. Obliquity, axial tilt. Earth's rotation axis is tilted relative to its orbital plane around the Sun. This tilt is responsible for seasons. When Northern Hemisphere is tilted towards Sun, it's summer there. When tilted away, it's winter. Current obliquity, 23,4 23°26. Obliquity range varies between 22.1 and 24.5 degram cycle period. 40,000 years effect on climate. Higher obliquity, more tilt. Stronger seasons, summer warmer, winter colder, at high latitudes. Weaker seasons, less contrast, at low latitudes. Poles receive more summer sunlight, less winter darkness. Equator receives slightly less solar energy overall. Lower obliquity, less tilt. Weaker seasons, summer cooler, winter warmer, at high latitudes. Stronger seasons at low latitudes. Poles receive less summer sunlight, more winter darkness. Equator receives slightly more solar energy overall. Key point: obliquity primarily affects seasonal contrast, especially at high latitudes. Lower tilt means cooler high-latitude summers, which favours ice sheet growth. Ice doesn't melt in summer. Current situation: obliquity is in middle range, duration 23 of 4 degree, and currently decreasing, moving toward 22.1 degree minimum over next 10,000 years. This will reduce seasonal contrast at high latitudes. 3. Precession, axial wobble. Earth's axis doesn't point in a fixed direction. It wobbles like a spinning top, tracing a circle in the sky over time. This wobble is called precession. Currently, Earth's axis points toward Polaris, North Star. In 13,000 years, it will point toward Vega. Cycle period: 26,000 years, one complete wobble. But precession's climate effects operate on 1,023,000 year timescale due to interaction with orbital precession. Effect on climate: precession determines which season occurs at perihelion, Earth's closest approach to Sun. Currently, perihelion occurs in early January, Northern Hemisphere, winter, Southern Hemisphere summer. Southern Hemisphere summer receives more solar energy, Earth closer to Sun. Northern Hemisphere summer receives less solar energy, Earth farther from Sun. In 11,000 years, half precession cycle. Perihelion will occur in July, Northern Hemisphere summer, Southern Hemisphere winter. Northern Hemisphere summer will receive more solar energy. Southern Hemisphere summer will receive less solar energy. Key point: precession affects which hemisphere receives more intense seasonal solar radiation. When Northern Hemisphere summer coincides with perihelion, summers are warmer and ice sheets melt more readily. When Northern Hemisphere summer coincides with aphelion, summers are cooler and ice sheets can grow. Current situation: Northern Hemisphere summers occur near aphelion, Earth far from Sun, making summers slightly cooler, favouring ice growth. Combined effects: these three orbital parameters vary independently on different timescales. Eccentricity, 100,000 years and 413,000 years. Obliquity, 41,000 years. Precession, 19,000, 23,000 years. The orbital variations combine to create complex patterns of solar energy distribution across latitudes and seasons. Milankovitch's insight: Milankovitch calculated the solar radiation received at 65° latitude during summer over the past 600,000 years, based on these orbital variations. His hypothesis: ice ages occur when high-latitude Northern Hemisphere summers receive less solar energy. Cool summers prevent winter snow from melting, allowing ice sheets to accumulate year after year. Key point: orbital variations don't significantly change total annual solar energy received by Earth. Changes are 1% in total. What changes is the distribution, how much energy reaches different latitudes in different seasons. Cool high-latitude summers, plus orbital configurations favouring ice growth. Glacial inception: warm high-latitude summers, plus orbital configurations favouring ice melt. Glacial termination, deglaciation. The 100,000-year problem. Milankovich's theory successfully predicts the 41,000-year cycle that dominated ice ages from 2.6 to 1 million years ago. This matches the obliquity cycle. But here's the problem: the 100,000-year eccentricity cycle is weak. Eccentricity changes cause only small variations in solar energy, 0.1 or 0.2% of total annual insolation. Yet the 100,000-year cycle dominates ice ages over the past million years, producing much larger climate changes than the weak eccentricity forcing alone could cause. This is called the 100,000-year problem, or eccentricity problem. Why does Earth's climate respond so strongly to weak eccentricity forcing, while responding less strongly to the more powerful obliquity and precession cycles? The answer: Eccentricity pacing must be amplified by feedback mechanisms within Earth's climate system. The orbital variations are the pacemaker, but internal Earth processes amplify the signal, converting small orbital changes into massive ice sheet growth and collapse. Feedback mechanisms, amplifying small changes. Orbital variations alone are insufficient to cause ice ages. The changes in solar energy distribution are too small, at most a few % difference in summer insolation at high latitudes. To transform these small, orbital nudges into massive ice sheets kilometers thick, feedback mechanisms must amplify the initial changes. Positive feedbacks amplifying. 1. Ice albedo feedback. Albedo is the reflectivity of a surface. Fresh snow while ice reflects. 80–90% of incoming solar radiation. Dark ocean water or vegetation absorbs just 90% of incoming solar radiation. The feedback, orbital configuration produces cool high-latitude summer. Winter snow doesn't melt completely. Snow persists into next winter, more snow accumulation. White snow ice reflects solar energy, surface absorbs less energy, stays cooler. Cool conditions preserve ice. Ice expands, more area covered by reflective ice. More reflection, even less solar absorption, more cooling, more ice growth. Positive feedback loop, ice creates conditions favouring more ice. Reversed during deglaciation, orbital configuration produces warm high-latitude summer. Ice snow melts dark ground, water exposed, absorbs more solar energy, warms further, warming melts more ice, more dark surface exposed, more absorption, more warming. Positive feedback loop, ice loss creates conditions favouring more ice loss. Quantitative importance. Ice albedo feedback is estimated to amplify orbital forcing by factor of 2 to 4x. Without this feedback, ice sheets would be much smaller. 2. Greenhouse gas feedback, CO2 and methane. Ice core data show CO2 and methane, CH4. Concentrations vary in lockstep with temperature. Glacial periods, CO2, 180, 200 ppm, CH4, 350, 400 ppb. Interglacial periods, CO2, KN 260, 280 ppm, CH4, 600, 700 ppb. The feedback, cooling, reduced CO2, CH4. Ocean cooling increases CO2 solubility. Ocean absorbs more CO2 from atmosphere. Atmospheric CO2 drops. Cooling reduces biological productivity. Less CO2 released from respiration decomposition. Cooling reduces wetland area. Less methane production from wetlands. Growing ice sheets alter ocean circulation. Changes CO2 exchange between surface and deep ocean. Lower CO2 CH4. More cooling. Lower greenhouse gas concentrations. Less infrared absorption. More heat escapes to space. Cooling. Cooling enables more ice growth. Warming. Increased CO2 CH4. Ocean warming reduces CO2 solubility. Ocean releases CO2 to atmosphere. Atmospheric CO2 rises. Warming increases biological productivity. More respiration decomposition. More CO2 release. Warming increases wetland area. More methane production. Changing ocean circulation releases CO2 from deep ocean to surface. Higher CO2, CH4. More warming. Higher greenhouse gas concentrations, more infrared absorption. Less heat escapes to space. Warming. Warming melts more ice. Quantitative importance. Greenhouse gas feedback amplifies orbital forcing by factor of 2, 3x. During deglaciation, CO2 rise from 190 to 280 pm. 90 ppm increase contributes duster kien protunsiskes of warming, a substantial fraction of the total 5-date glacial interglacial temperature change. Important question. Does temperature change cause CO2 change, or does CO2 change cause temperature change? Answer. Both. In most cases, orbital forcing initiates temperature change, then CO2 responds, ocean outgassing uptake. Then CO2 change amplifies the temperature change further. It's a feedback loop, not a simple cause-effect chain. 3. Vegetation feedback. Vegetation affects albedo and moisture. Dark forests absorb more solar energy than light-coloured grasslands or bare ground. Vegetation affects evapotranspiration, water release, influencing regional climate. The feedback. Cooling. Vegetation changes. As climate cools, forests retreat, replaced by tundra or ice. Lighter surface increases albedo, more cooling. Reduced evapotranspiration alters precipitation patterns. Warming. Vegetation changes. As climate warms, forests expand northward. Darker surface decreases albedo, more warming. Increased evapotranspiration alters precipitation patterns. Quantitative importance. Smaller than ice albedo or greenhouse gas feedbacks, but still significant, especially at mid-latitudes. 4. Ocean circulation feedback. Ocean currents redistribute heat globally. Changes in ocean circulation can amplify climate changes. Thermohaline circulation, THC. Deep ocean circulation driven by density differences, temperature and salinity. Warm, salty water flows northward at surface, e.g., Gulf Stream, releases heat to atmosphere, becomes cold and dense, sinks in North Atlantic, flows southward at depth, eventually upwells and returns to surface. The feedback. During glacial inception, ice sheet growth releases fresh water from precipitation that becomes ice rather than returning to ocean. Sea level drops, ice shelves form, insulating ocean from atmosphere. Changes in freshwater input and temperature alter. THC, weakened THC, less heat transported northward. Northern hemisphere cools more. More cooling enables more ice growth. During deglaciation, ice sheet melting adds massive fresh water to North Atlantic. Fresh water is less dense than salt water, reduces deep water formation. THC weakens or shuts down temporarily. Complex effects on regional climate. Quantitative importance. THC changes can cause rapid regional climate shifts, several degrees over decades to centuries. May be responsible for abrupt climate changes during glacial periods. 5. Dust and aerosol feedback. Glacial periods are dustier than interglacials. Ice cores show 10-20x higher. Dust concentrations during glacials. Sources: expanded deserts, exposed continental shelves, glacial grinding, rock flow from glaciers, reduced vegetation cover. The feedback: cooling, more dust, drier. Climate expands deserts. Lower sea levels expose continental shelves, new dust sources, stronger winds from greater temperature gradients, less vegetation to stabilize soil. More dust, complex climate effects. Dust in atmosphere reflects solar energy. Cooling, direct effect. Dust on ice reduces albedo. Warming, indirect effect. Dust fertilizes ocean with iron, increases phytoplankton, draws down CO2. Cooling, indirect biological effect. Net effect, probably amplifies cooling, but magnitude is debated. 6. Sea ice feedback. Sea ice formation melting provides another amplifying feedback. Cooling, more sea ice, ocean surface freezes. High albedo sea ice reflects solar energy. More cooling. Sea ice insulates ocean from atmosphere. Ocean retains heat while atmosphere cools. Complex effects. Warming. Less sea ice. Sea ice melts. Dark ocean water exposed. Absorbs solar energy. More warming. Quantitative importance. Significant in polar regions. Contributes to Arctic amplification. Arctic warming faster than global average. Negative feedbacks, stabilizing. Not all feedbacks amplify changes, some provide stability. 1. Planck feedback, blackbody radiation. Warmer objects radiate more infrared energy, Stefan Boltzmann law. The feedback. Surface warms, radiates more energy to space, cooling effect. Surface cools, radiates less energy to space, retains more heat. This is the primary stabilizing feedback preventing runaway warming or cooling. It's why Earth doesn't experience runaway greenhouse effect like Venus or snowball Earth, except during rare extreme events in deep past. 2. Water vapor feedback, complex. Water vapor is a greenhouse gas, but also forms clouds which reflect solar energy. Warming, more evaporation, more water vapor, more greenhouse effect. Warming, positive feedback, but also more water vapor, more clouds, reflects solar radiation. Cooling, negative feedback. Net effect, debated. Most evidence suggests water vapor feedback is net positive, amplifies warming, but clouds provide some negative feedback. The combined effect. Multiple positive feedbacks amplify orbital forcing. Ice albedo, 2 to 4x amplification. Greenhouse gases, 2 to 3x amplification. Vegetation, 1.2, 1.5x amplification. Ocean circulation, variable, sometimes large regional effects. Dust aerosol, 1.1, 1.3x amplification. Total amplification. The combination of feedbacks amplifies weak orbital forcing by factor from 5 to 10x, converting 1 to 2 degree Celsius orbital-driven temperature changes into 5 or 8 degree total glacial interglacial temperature swings. This explains how small orbital variations produce large climate changes, but it still doesn't fully explain the 100,000-year cycle dominance. The 100,000-year mystery. Why this cycle dominates. Despite Milankovitch's success in explaining the orbital pacing of ice ages, a fundamental mystery remains. Why does the weak 100,000-year eccentricity cycle dominate ice ages over the past million years, when eccentricity has the smallest direct effect on solar radiation? The 41,000-year obliquity cycle has much stronger direct forcing, yet it produces smaller climate responses. The 20,000-year precession cycles are also stronger than eccentricity, yet the 100,000-year cycle dominates. Several hypotheses attempt to explain this. Hypothesis 1. Eccentricity modulates precession. Eccentricity doesn't directly cause much climate change, but it modulates the amplitude of precession's effect. The mechanism. Precession determines which season occurs at perihelion. But perihelion only matters if the orbit is elliptical. If orbit is nearly circular, low eccentricity, perihelion versus aphelion makes little difference because Earth is roughly the same distance from Sun all year. When eccentricity is high, orbit is more elliptical. Perihelion-aphelion distance difference is large. Precession has strong effect. Big difference whether summer occurs at perihelion or aphelion. When eccentricity is low, orbit is nearly circular. Perihelion-aphelion distance difference is small. Precession has weak effect. Little difference when summer occurs. Implication: eccentricity acts as an envelope, modulating precession's strength. Over a 100,000-year eccentricity cycle, precession's climate impact varies from strong to weak, and back to strong. This creates a 100,000-year envelope in climate response even though eccentricity itself has weak direct forcing. Assessment. This explains part of the 100,000-year signal but not all. The amplitude of the 100,000-year cycle is still larger than this modulation effect alone would predict. Hypothesis 2. Ice sheet dynamics and nonlinear response. Ice sheets don't grow and shrink linearly in response to orbital forcing. They exhibit complex nonlinear behavior with thresholds, feedbacks, and time lags. The mechanism: ice sheet growth is asymmetric. Growth: glacial inception. Slow process taking tens of thousands of years. Snow accumulates gradually, compresses to ice sheet thickens and spreads. Rate limited by snowfall rates and ice flow dynamics. Collapse: deglaciation. Can be rapid, thousands of years or less. Once melting exceeds snowfall, ice sheets thin, lowering their elevation, exposing them to warmer temperatures at lower altitudes, accelerating melting. Feedback creates rapid collapse. Ice sheets have internal dynamics. Advance. Ice flows outward under its own weight. Larger ice sheets flow faster, more mass pushing outward. Calving. When ice sheets reach ocean, they can collapse catastrophically as icebergs break off. Isostatic adjustment. Ice sheet weight depresses Earth's crust. When ice melts, crust rebounds. These processes create time lags and complex interactions. Nonlinear thresholds. Ice sheet growth may require sustained cooling beyond a threshold. Once started, growth continues even if forcing weakens slightly, hysteresis. Collapse requires sustained warming beyond a threshold. The 100,000-year connection. Ice sheets might integrate forcing over multiple precession and obliquity cycles. Several favorable precession obliquity cycles. Ice sheet grows, eventually reaches maximum size, constrained by geography, isostasy, ice flow dynamics. Persists through several unfavorable orbital cycles. Ice sheet is now self-sustaining due to feedbacks. Eventually, an exceptionally favorable orbital configuration triggers rapid collapse. The time required for ice sheets to grow to maximum size and persist creates a 100,000-year timescale assessment. This explains the asymmetry, slow growth, rapid collapse, and potentially explains why ice sheets respond on a 100,000-year timescale, even though forcing is on shorter timescales. However, the exact mechanisms are still debated. Hypothesis 3. Carbon cycle changes. The CO2 changes during glacial interglacial cycles are large, 190 ppm to 280 ppm, and occur in phase with temperature changes, suggesting CO2 plays an important amplifying role. But where does the CO2 go during glacials, and why does it change on a 100,000-year timescale? Possible mechanisms: ocean circulation changes. During glacials, deep ocean circulation weakens, storing more CO2 in deep ocean, reducing atmospheric CO2. Ocean temperature: colder ocean absorbs more CO2. Biological pump: changes in ocean biology, phytoplankton productivity, especially in Southern Ocean, affect CO2 drawdown. Iron fertilization from increased glacial dust might enhance biological productivity, drawing down CO2. Ocean stratification: changes in ocean mixing affect CO2 exchange between surface and deep ocean. The 100,000-year connection: if ocean carbon storage responds non-linearly to orbital forcing, with thresholds and long-time constants, it might create 100,000-year periodicity in atmospheric CO2, which then drives 100,000-year climate cycles through greenhouse effect. Assessment: CO2 changes are important amplifiers, but the mechanisms controlling CO2 on a 100,000-year timescale are not fully understood. This is an active area of research. Hypothesis. 4. Lithosphere, rock cycle, effects. Over glacial cycles, massive ice sheets depress Earth's crust, isostasy. When ice melts, crust rebounds. This creates geological effects that might influence ice age cycles. Proposed mechanisms: volcanic activity. Crustal rebound after deglaciation might trigger volcanic eruptions releasing CO2, contributing to warming. Sediment and dust. Glacial grinding produces rock flour that weathers chemically, consuming CO2. Changes in weathering rates might affect atmospheric CO2 on 100,000-year timescales. Geothermal heat. Ice sheet dynamics might be affected by geothermal heat flux through crust, which could vary with isostatic adjustments. Assessment. These effects are probably minor compared to other mechanisms but might contribute. Highly speculative. Hypothesis 5. Stochastic resonance. Perhaps the 100,000-year cycle emerges from the interaction of the three orbital cycles, eccentricity, obliquity, precession, with random climate variability. The mechanism: climate system has internal variability, random fluctuations from weather, ocean variability, volcanic eruptions, etc. When this noise interacts with periodic orbital forcing, it might preferentially amplify certain frequencies. Mathematical phenomenon. Stochastic resonance occurs in nonlinear systems where noise can enhance response to weak periodic signals. The system might skip some precession cycles, responding only to every fourth or fifth one, creating appearance of longer cycle. The 100,000-year connection. The combination of three orbital cycles, 100K, 41K, 20K, plus nonlinear climate response plus internal variability, might naturally produce dominant 100,000-year rhythm, even though no single forcing operates exactly at that frequency. Assessment. Mathematically possible and might contribute, but doesn't fully explain observations, still requires invoking complex internal climate dynamics. Hypothesis. 6. Astronomical forcing changes, mid-Pleistocene transition. Around 1 million years ago, the dominant cycle shifted from 41,000 years, obliquity, to 100,000 years, eccentricity. What changed? Important. The orbital parameters didn't change. They operate on predictable cycles determined by celestial mechanics. What changed was Earth's climate response to those cycles. Possible explanations for the mid-Pleistocene transition: ice sheet size threshold. Before 1 million years ago, ice sheets were smaller. Around 1 million years ago, ice sheets began growing larger, perhaps because gradual cooling trend over past few million years finally allowed ice sheets to reach size where internal dynamics became important. Once ice sheets reach certain size, their dynamics dominate climate response, creating 100,000-year pacing regolith removal. Over multiple glacial cycles, ice sheets scrape away soil and loose rock, regolith, exposing bedrock. Ice sheets on bedrock slide more easily and are less stable, potentially allowing them to grow larger before collapsing. First few ice ages removed regolith. Subsequent ice ages occurred on bedrock with different dynamics. CO2 threshold, gradual decline in background CO2 levels from long-term geological processes like weathering and carbon burial, might have crossed threshold around 1 million years ago, allowing more extreme glaciations. Assessment. The mid-Pleistocene transition demonstrates that ice age dynamics can change over time. Understanding this transition is key to understanding the 100,000-year cycle. Current scientific consensus. The 100,000-year cycle likely results from a combination of eccentricity modulation of precession, nonlinear ice sheet dynamics with long-time constants, carbon cycle feedbacks operating on a 100,000-year timescale, possible stochastic resonance effects. No single explanation is sufficient. The 100,000-year cycle emerges from the complex interaction of orbital forcing, climate feedbacks, ice sheet dynamics, and carbon cycle changes. This is still an active research area. While we understand the pieces, we don't fully understand how they interact to produce the observed 100,000-year dominance. Life during ice ages. Human evolution in the freezer. Humans evolved during the ice age. Our entire evolutionary history as the genus Homo, past 2 to 3 million years, occurred during the Quaternary glaciation, when Earth repeatedly cycled between glacial and interglacial states. This raises fascinating questions. How did ice ages affect human evolution? Did the climate instability drive selection for intelligence and adaptability? How did our ancestors survive the extreme conditions? Timeline of human evolution during the Ice Age. 2.6 million years ago. Quaternary glaciation begins. First glacial cycles with 41,000-year periodicity. Genus Homo emerges in Africa around this time. Homo habilis, Homo erectus. 2 million years ago, Homo erectus spreads beyond Africa into Asia and eventually Europe, develops more sophisticated tools, Acheulean hand axes, learns to control fire. 1 million years ago, mid-Pleistocene transition, Ice Age cycles shift to 100,000-year periodicity with more extreme glaciations. Homo erectus populations exist across Africa, Asia, Europe. 700,000, 300,000 years ago, Homo heidelbergensis, ancestor of Neanderthals and modern humans, spreads across Africa, Europe, and Western Asia, brain size increasing toward modern levels. 40,000 years ago, Neanderthals, Homo neanderthalensis, occupy Europe and Western Asia during glacial and interglacial periods, highly adapted to cold climates. 300,000 years ago, Homo sapiens emerges in Africa. 200,000 to 70,000 years ago, anatomically modern humans in Africa, not yet dispersed globally. 70,000 years ago, Toba supervolcano eruption. Human population crashes to perhaps 3,000, 10,000 individuals, genetic bottleneck. 70,000, 50,000 years ago, behavioral modernity emerges, sophisticated language, art, complex tools. Humans begin dispersing out of Africa. 50,000, 10,000 years ago, humans spread across entire world during last glacial period. Reach Australia, 50,000 years ago, Europe, just 40,000 years ago, Americas, 15,000 to 20,000 years ago. Megafauna extinctions follow human arrival in each continent. 26,000, 19,000 years ago, last glacial maximum, ice sheets at maximum extent. Humans survive in refugia and ice-free regions. 19,000, 11,700 years ago, deglaciation, rapid warming, ice sheets retreat, sea levels rise, human populations expand into previously glaciated regions. 11,700 years ago, Holocene interglacial begins, climate stabilizes, agriculture develops. 10,000 years ago, civilization emerges, thus 1,000 years ago. Key point: all of human evolution occurred during unstable, oscillating climate. The warm, stable Holocene, past 11,700 years, during which civilization developed, is anomalous. A brief calm period unlike the chaotic climate our ancestors experienced for millions of years. Did ice ages drive human intelligence? Hypothesis: climate instability selected for intelligence, behavioral flexibility, and cultural innovation. The argument: stable environments favor specialization. Species can evolve narrow adaptations to specific conditions. Example: koalas specialize to eat eucalyptus leaves. Unstable environments favor generalization. Species that can adapt rapidly to changing conditions have advantage. Behavioral flexibility, learned adaptations, is faster than genetic evolution. Ice ages created extremely unstable environments, climate swinging between glacial and interglacial every 100,000 years. Within each glacial cycle, numerous abrupt climate shifts, Dansgaard-Oeschger events, temperature swings of 5 Tessatendegger over decades, dramatic ecosystem changes, forests, grasslands, tundra, ice sheets and back, megafauna extinctions and species turnovers, changing resource availability, species that survived these changes needed, behavioral flexibility, change strategies as conditions change, social cooperation, coordinate to hunt, defend against predators, survive harsh conditions, cultural transmission, teach successful strategies to offspring, problem-solving ability, adapt tools and techniques to new situations. All of these traits characterize human intelligence. Evidence supporting this hypothesis: brain size increase. Hominin brain size increased dramatically over past 2 million years during Ice Age. Homo habilis, 600 cc Homo erectus, 900 cc Homo heidelbergensis, 250 cc Neanderthals, 500 cc Homo sapiens, or 350 cc. This increase occurred during the Ice Age's climate instability. Technological innovation. Tool complexity increased over time. Humans developed diverse toolkits specialized for different tasks. Composite tools, spear with stone point attached to wooden shaft, projectile weapons, atlatls, bows, clothing and shelters, fire control art and symbolic expression. These innovations suggest increasing cognitive sophistication, geographic expansion. Humans successfully colonized diverse environments from Arctic tundra to tropical rainforests to deserts, demonstrating behavioral flexibility. Counterarguments. Correlation isn't causation. Brain size increase during Ice Age doesn't prove Ice Ages caused it. Other factors, social competition, dietary changes, etc., might be responsible. Many species survived Ice Ages without large brains. Megafauna like mammoths, bison, reindeer survived multiple glacial cycles without evolving human-like intelligence. Brain size stopped increasing. Over past 20,000 years, including Holocene, human brain size has actually decreased slightly, less than 10%, even though climate stabilized. This suggests brain size isn't simply tracking climate instability. Assessment. Ice ages likely played a role in human evolution by creating selective pressures favoring flexibility and intelligence, but were probably not the only factor. Human evolution is multifactorial. Climate, diet, social structure, sexual selection, and other factors all contributed. How did humans survive Ice Ages? During glacial periods, conditions were harsh. Global temperature 5 to colder ice sheets covering regions where millions now live sea levels 120-130 meters lower. Forests replaced by grasslands, tundra, or ice megafauna present but under stress. Human survival strategies, refugia. During glacial maxima, humans survived in ice-free regions. Southern Europe, Mediterranean refugia, Central Asia, Africa, less affected by ice but had different climate challenges. Southeast Asia, Bering Land Bridge region, technological adaptations, warm clothing sewn from animal hides, shelters, caves, constructed dwellings, tents, fire, heating, cooking, light, hunting tools optimized for megafauna social cooperation, dietary flexibility. Humans are omnivores capable of eating diverse foods. Megafauna hunting, mammoths, bison, reindeer. Smaller game fish and shellfish plant foods were available, scavenging when necessary. Population dynamics. Genetic evidence shows multiple population bottlenecks during glacial periods. Populations expanded during interglacials. Geographic isolation during glacials. Ice sheets and deserts separated populations. Gene flow during interglacials, populations reconnected. Neanderthal extinction. Neanderthals went extinct 40,000 years ago during the last glacial period. Possible causes: competition with Homo sapiens, who entered Europe 145,000 years ago, climate change, abrupt cooling events, small population size, genetic bottleneck, absorption, interbreeding with H. sapiens. Most likely, a combination of factors during a time of climate stress. The Holocene. An unusually stable period. For the past 11,700 years, Earth has been in an interglacial period, the Holocene, with remarkably stable climate. Temperature varied by only the globally. No ice age advances, predictable seasonal patterns, stable sea levels. This stability enabled agriculture, requires predictable climate, permanent settlements, population growth, civilization. All of human civilization developed during the Holocene's climatic stability. Before the Holocene, humans were hunter-gatherers surviving climate chaos. During the Holocene, humans became farmers, city builders, and eventually industrial civilization. The key insight: the climate we consider normal is actually abnormal. A brief warm period in a planet whose dominant state for the past million years has been glaciation. The current interglacial. Where are we in the cycle? Understanding where we are in the current glacial interglacial cycle is essential for predicting future natural climate change, and for understanding how human activities might be affecting the cycle. The Holocene interglacial, 11,700 years ago, present. Characteristics: began with rapid warming. 19,000 millions or 11,700 years ago, termination on 1. Ice sheets retreated from maximum extent. Sea levels rose 130 meters. Global temperature increased 5 to 8 degrees from glacial maximum. Climate stabilized 700 years ago. Holocene climate has been remarkably stable compared to glacial periods. Temperature variations, degrees globally. No return to glacial conditions. Gradual cooling trend over past 8,000 years, until recent. Anthropogenic warming, early Holocene, 11,700, 8,000 years ago. Continued warming, Holocene climate optimum, whereas 9,000 and 5,000 years ago. Global temperatures perhaps 1 to 2 degrees warmer than late 20th century Sahara, was green, African humid period. Human populations expanded mid-Holocene, 8,000, 4,000 years ago. Gradual cooling begins Sahara desiccation, 500 to 5,000 years ago. Agricultural civilizations develop, Mesopotamia, Egypt, Indus Valley, China. Late Holocene, 4,000 years ago, 1850 CE. Gradual cooling continues. Various climate fluctuations. Medieval warm period, Little Ice Age. Overall trend toward cooler conditions, though still much warmer than glacial periods. Modern period, 1850 CE. Present. Rapid warming from anthropogenic greenhouse gas emissions. Temperature increase. 1.0 study since pre-industrial rate of warming unprecedented in Holocene. Comparing to previous interglacials, Eemian interglacial, well 30,000 or 115,000 years ago. Last interglacial before current one, duration, 15,000 years. Peak temperatures, 1 times warmer than present. Early Holocene. Sea levels, 4 to 6 meters higher than present. Less ice in Greenland and Antarctica. Ended with return to glacial conditions. Other recent interglacials, MS11, 4 to 20,000, 380,000 years ago, lasted 40,000 years, unusually long. MS9, there was 1,000, 320,000 years ago, lasted 20,000 years. MS7, 245,000, 190,000 years ago. Complex multiple warm peaks. Typical interglacial duration, 10,000, 20,000 years. Current interglacial Holocene duration, 11,700 years. Implication: based on previous interglacials, the Holocene is approaching typical interglacial length. Natural progression would suggest we're approaching the end of the interglacial, and should be transitioning back toward glacial conditions within the next few thousand years. Orbital configuration and the next ice age. Current orbital parameters, 2025. Eccentricity, 0.67. Low, decreasing. Obliquity, 23.44. Middle range, decreasing. Precession phase, Northern Hemisphere. Summer occurs near aphelion, Earth far from Sun. Trends, Eccentricity will continue decreasing for 125,000 years, orbit becoming more circular. Obliquity will continue decreasing for 10,000 years, currently at 23.4 heading toward 22.1 minimum. Precession. Northern Hemisphere, summers will start occurring closer to perihelion in 11,000 years. What do these trends mean for glaciation? Favouring glaciation, cooling, low eccentricity, orbit nearly circular, decreasing obliquity, weaker high latitude seasons, current precession phase, NH summer at aphelion. Based on orbital parameters alone, we should be in a period favouring ice sheet growth. Conditions are similar to previous glacial inceptions, but we're not cooling, we're warming rapidly due to human greenhouse gas emissions, the anthropogenic disruption. Without human influence, natural progression based on orbital cycles and previous interglacial patterns suggests gradual cooling over next few 1,000 years glacial inception, beginning of next ice age, within 1,000–5,000 years, full glacial conditions within 10,000–20,000 years. With human influence, current CO2 levels, 420 ppm, are higher than any time in past 3+ million years. Warming of 1.2 to C so far, with more warming in the pipeline from already emitted greenhouse gases. Projected warming of 2 to 4 degrees by 2100 depending on future emissions. The key question: have humans delayed or prevented the next ice age? Research findings. Rudderman hypothesis, 2003. Anthropologist William Rudderman proposed that humans began affecting climate 8,000 years ago through agriculture. Forest clearance released CO2, rice paddies produced methane. These early emissions prevented glacial inception that would have occurred naturally. Controversial but influential idea. Recent studies, 2016, Ganopolsky et al. Climate models suggest, without anthropogenic CO2, next ice age would begin within 1,500 years. With current CO2 levels, 420 ppm, next ice age is delayed by at least 50,000 years. If CO2 reaches 600 ppm, possible under high emission scenarios, next ice age might be prevented entirely for 100,000+ years. Implication: human greenhouse gas emissions have fundamentally disrupted the natural ice age cycle. We've skipped the next ice age. Is this good or bad? Arguments that preventing ice age is good. Ice ages are harsh. Billions would be displaced by advancing ice sheets. Agricultural disruption would be severe. Sea level drop would alter coastlines and ecosystems. Preventing ice age protects current human civilization. Arguments that preventing ice age is bad. Natural climate cycles are part of Earth system. Disrupting them has unknown consequences. Current warming rate is extremely rapid, 100x faster than natural deglaciation. Rapid warming causes sea level rise, extreme weather, ecosystem disruption, species extinctions, agricultural challenges. We're conducting an uncontrolled experiment on Earth's climate system. Most climate scientists view preventing the next ice age, 50,000 years away, is not the immediate concern. Rapid warming over next centuries is the immediate concern. Current warming rate and magnitude exceeds natural variability. Impacts of rapid warming outweigh any benefit of preventing distant future ice age where we are in the cycle. Natural progression without humans. Near the end of current interglacial, approaching transition to next glacial period within few thousand years. Actual situation with human influence. In anthropogenically induced warming period that has overridden natural cooling trend and prevented delayed next ice age by tens of thousands of years. We've broken out of the 100,000-year cycle, at least for now. Abrupt climate change. The dangerous instability. While the 100,000-year glacial interglacial cycle is the dominant pattern, it's not smooth. Within each cycle, especially during glacial periods, climate experienced numerous abrupt shifts, temperature changes of 5 or 10 degrees over decades to centuries. These abrupt changes demonstrate that Earth's climate system can flip rapidly between states, a disturbing finding with implications for future climate change. Dansgaard-Oeschger, DO events. During the last glacial period, roughly 110,000–11,700 years ago, Greenland ice cores showed 25 abrupt warming events called Dansgaard-Oeschger events, named after the scientists who discovered them. Characteristics: rapid warming, 8 to 16 days in Greenland over decades, possibly as fast as a single decade. Warmth persisted for centuries to millennia. Gradual cooling followed, then abrupt return to cold conditions, recurrence interval. DO events occurred every 1,500 years on average during glacial periods, though spacing varied. Geographic extent: initially thought to be regional, North Atlantic Chia, Greenland, but evidence now shows global impacts, though most pronounced in Northern Hemisphere. Cause: not fully understood, but most likely related to changes in Atlantic Ocean circulation, thermohaline circulation de Roambe, Atlantic meridional overturning circulation. Proposed mechanism: normal glacial state, cold North Atlantic, limited deep water formation, weak AMOC. Triggering event: possibly changes in ice sheet carving, freshwater input, or internal ocean dynamics. AMOC suddenly strengthens, more heat transported northward. North Atlantic and surrounding regions warm rapidly. Greenland warms 8 to 16 degrees. Warm state persists for centuries to millennia until conditions change. Return to cold state. AMOC weakens, possibly from freshwater input from melting ice. Heat transport decreases, rapid cooling back to cold state key point. These were not gradual changes. They were abrupt flips between quasi-stable states, demonstrating that climate system has thresholds and tipping points. Heinrich events. Even more dramatic than DO events, Heinrich events involved massive iceberg discharges from North American ice sheet, Laurentide ice sheet. Characteristics: massive armadas of icebergs floated across North Atlantic. Icebergs melted, dropping debris, ice-rafted debris IRD on ocean floor, created layers of coarse sediment visible in ocean cores, associated with severe cooling in North Atlantic region. Occurred every 7,000, 10,000 years during glacial periods. Cause: ice sheet instability, possibly related to accumulation of water at base of ice sheet lubricating flow, causing rapid ice discharge. Impact: massive freshwater input to North Atlantic, disruption of AMOC thermohaline circulation, severe regional cooling, atmospheric circulation changes affecting global climate. 6. Heinrich events occurred during last glacial period, labelled H1H6, with H1 being most recent 16,000 years ago during deglaciation. Bond cycles. DO events and Heinrich events are related in a pattern called bond cycles. Series of DO events, warming-cooling oscillations, culminating in Heinrich event, massive iceberg discharge, and severe cooling. Pattern repeats. This suggests underlying pacing mechanism for abrupt climate change during glacial periods, though the exact mechanism remains debated. The Younger Dryas, the most recent and well-studied abrupt climate change event, occurred during deglaciation. Timing: 12th 900, 11th 700 years ago. What happened? Earth was warming out of last glacial period. Around 12th 900 years ago, abrupt return to near-glacial conditions in Northern Hemisphere. Temperatures in Greenland dropped 10 to 15% over decades. Glaciers re-advanced in many regions. Cold, dry conditions persisted for 700 years. Around 11,700 years ago, equally abrupt warming, possibly as fast as a decade. Holocene interglacial began. Cause: most likely disruption of AMOC by fresh water from melting ice sheets. As North American ice sheet melted, enormous volumes of meltwater accumulated in glacial lakes. Around 12th 900 years ago, ice dam failed, releasing fresh water into North Atlantic, or possibly Arctic Ocean first, then into North Atlantic. Massive freshwater input disrupted AMOC-reduced heat transport to high northern latitudes. Abrupt cooling. Alternative hypothesis. Younger Dryas impact hypothesis proposes asteroid-comet impact triggered the event. Controversial, lacking clear evidence. Impact on humans. Megafauna extinctions in North America coincide with Younger Dryas. Clovis. Culture disappears from archaeological record. Climate stress on human populations. Possible stimulus for agricultural development as response to climate-induced resource scarcity. The key lesson from abrupt climate change is climate can change much faster than the 100,000-year cycle suggests. While the overall glacial-interglacial cycle takes tens of thousands of years, regional and sometimes global climate can flip between states in decades or less. This happens through threshold effects and positive feedbacks. Gradual changes accumulate until system crosses threshold. Sudden reorganization to new state, tipping point. New state maintained by feedbacks. System can flip back if forcing reverses or another threshold is crossed. Implications for current climate change. Are there tipping points in current warming? Potential tipping elements in current climate system. 1. Atlantic meridional overturning circulation, AMOC, collapse. Greenland ice sheet melting adds fresh water to North Atlantic. Fresh water reduces density, inhibits deep water formation. AMOC weakens or shuts down regional cooling in North Atlantic region. Despite global warming, global climate impacts, shifts in tropical rain belts, increased storms, etc. Current status. AMOC has weakened by zo'n 15 to 20% since 1950s. Models suggest continued weakening under warming scenarios. Complete collapse considered possible but not imminent. Low probability this century but increasing risk. 2. Greenland ice sheet collapse. Accelerated melting underway. If summer temperatures remain above threshold, ice sheet could become unstable. Complete melting would raise sea level 7 meters. Timescale. Centuries to millennia, but could be irreversible once threshold crossed. Current status. Greenland losing 180 billion tons of ice per year and accelerating. Some studies suggest threshold may have been crossed or is imminent. 3. West Antarctic ice sheet, WAIS. Collapse. WAIS is marine ice sheet, sitting on bedrock below sea level. Vulnerable to warm ocean water undermining ice shelves. Collapse could be rapid once triggered, decades to centuries. Complete collapse would raise sea levels 3-5 meters. Current status. WAIS showing signs of instability. Some glaciers, Thwaites Glacier, already in irreversible retreat. 4. Amazon rainforest dieback. Amazon rainforest creates its own rainfall through evapotranspiration, deforestation plus warming. Plus drought could push system past threshold. Forest dies back, replaced by savanna, massive carbon release, reduced rainfall, biodiversity loss. Current status. Amazon experiencing increased droughts and fires. System showing reduced resilience. 5. Arctic sea ice loss. Summer. Arctic sea ice declining rapidly. Ice-free Arctic summers possible within decades. Ice albedo feedback accelerates Arctic warming impacts on weather patterns. Ecosystems current status. Arctic warming 2-3x faster than global average. Summer sea ice extent down 40% since 1980s. 6. Permafrost thaw. Permafrost contains enormous amounts of carbon, twice current atmospheric CO2. Warming thaws permafrost, releasing CO2 and methane. Positive feedback. Warming, thaw, emissions, more warming. Current status. Permafrost thawing observed across Arctic. Emissions increasing but magnitude uncertain. The concern. Unlike the gradual 100,000-year cycle, these tipping points could trigger within decades to centuries, producing rapid, difficult-to-reverse changes. The paleoclimate record, Dio events, Heinrich events, Younger Dryas, demonstrates that rapid climate change is possible. Earth's climate system has thresholds and tipping points. When crossed, change can be abrupt. Current warming is pushing multiple systems toward their tipping points simultaneously. The next ice age. Will it happen? Based on natural cycles, Earth should be approaching the next ice age within the next few thousand years. But human greenhouse gas emissions have likely delayed or prevented this. Let's explore the scenarios. Scenario 1. Natural progression, counterfactual, no humans. Orbital configuration, favourable for glacial inception over next few thousand years. Expected progression, gradual cooling over next 1,000-3,000 years. Northern Canada and Scandinavia accumulate snow that persists year-round. Snow compresses to ice, forming nascent ice sheets. Ice albedo feedback amplifies cooling, CO2 decreases, ocean uptake, amplifying cooling further. Ice sheets expand over next 10,000-20,000 years. By 30,000-50,000 years from now, full glacial conditions, ice sheets covering Canada, northern USA, northern Europe, northern Asia, global, temperature 5 to 8 degrees colder than present sea level 100-130 meters lower. Ecosystems shifted toward equator humans, if still existing, living in refugia, technologically adapted or migrated. This was the natural trajectory until humans intervened. Scenario 2. Low anthropogenic emissions, hypothetical. If humanity had maintained pre-industrial CO2 levels, just 280 ppm, expected progression, gradual cooling begins as orbital forcing favours glaciation. By 1,000–2,000 years from now, perceptible cooling in high northern latitudes. By 5,000 years from now, glacial inception underway. By 10,000–20,000 years from now, progressing toward full glacial conditions. This scenario is no longer possible. We've already emitted too much CO2. Scenario 3. Current emissions trajectory, moderate. Current CO2 levels, 420 ppm and rising. Projected peak, if emissions decline this century, 500–600 ppm. Expected progression. CO2 remains elevated for thousands of years. CO2 removal from atmosphere is slow. Natural processes take 10,000 plus years to reduce atmospheric CO2. Elevated CO2 prevents cooling that would initiate glaciation. Next ice age delayed by at least 50,000 years, possibly 100,000 plus years. Eventually, after 50,000–100,000 years, CO2 naturally returns to lower levels through weathering and ocean uptake. Orbital configuration at that future time determines if, when glaciation resumes. This is the likely scenario based on current trajectories. Scenario 4. High emissions, worst case. If emissions continue unabated, CO2 could reach 800–200 ppm by 2100. Expected progression. Sustained high CO2 for tens of thousands of years. Next ice age delayed by 100,000 plus years. Might skip entire 100,000 year cycle. Eventually CO2 declines through natural processes. Ice age cycle might resume after 100,000–200,000 years. This scenario represents fundamental disruption of the natural cycle. Scenario 5. Runaway warming extreme. If positive feedbacks, permafrost thaw, methane release, etc., cause warming to exceed projections, possible outcomes: prolonged superinterglacial lasting hundreds of thousands of years, complete melting of Greenland and West Antarctic ice sheets, sea level rise. 10 plus meters, fundamentally different climate state ice age cycle disrupted for hundreds of thousands of years. This scenario is considered unlikely but not impossible. What determines which scenario unfolds? Human choices over the next century. If we rapidly reduce emissions, net zero by 2050–2070, deploy carbon removal technologies, limit warming to 1.5°C, then, scenario 3, moderate delay of next ice age by 50,000 plus years, manageable near-term impacts. If we continue high emissions through 2100, exceed 3°–4°C warming, trigger multiple tipping points, then, scenario 4 or 5, major disruption of ice age cycle, severe near-term impacts. The key insight: short-term versus long-term effects are different. Short-term, next centuries, rapid warming is the problem. Ice age prevention is irrelevant because next ice age is thousands of years away. Long-term, next 10,000–100,000 years. We've disrupted the natural ice age cycle with unknown consequences for Earth's climate system evolution. Should we worry about preventing the next ice age? Arguments: this is not a concern. Next ice age is 1,000–5,000 years away naturally, not an immediate threat. Current warming causes immediate severe problems. Future civilizations, if any, will have technology to manage climate. Natural ice ages are slow, thousands of years. Plenty of time to adapt arguments. This is a concern. Disrupting natural cycles has unpredictable consequences. We don't fully understand long-term feedbacks. Earth's system might respond in unexpected ways. We're conducting an irreversible experiment. Most climate scientists position preventing next ice age is not the primary concern. Rapid anthropogenic warming over next centuries is the immediate challenge. Long-term ice age cycle disruption is interesting scientifically but not actionable. We need to focus on managing current warming. Future ice ages. Eventually, teens to hundreds of thousands of years from now, CO2 will return to lower levels through natural processes and orbital configurations will again favour glaciation. Ice Age cycles will likely resume, unless human civilization persists and actively manages climate long-term. Earth's climate system has been fundamentally altered in ways we don't understand. Tipping points create new quasi-stable states. The Ice Ages aren't gone forever. They're paused. Living on an Ice Age planet. Philosophical and practical implications. Understanding that Earth regularly freezes every 100,000 years, and that we're living in a brief warm interval, provides profound perspective on climate, humanity, and our relationship with Earth's natural cycles. Implication of 1. Climate is never stable. Popular misconception: climate should be stable, and human-caused change is uniquely disruptive. Reality: climate has always changed, often dramatically. The 100,000-year cycle shows climate is inherently dynamic. However, natural changes are typically gradual, thousands to tens of thousands of years, giving ecosystems and species time to migrate, adapt, or evolve. Current anthropogenic warming is extremely rapid, decades to centuries, 10 to 100x faster than natural changes. The distinction matters. Both natural and human-caused climate change are real, but their rates and mechanisms differ. Natural changes don't excuse human-caused changes, but understanding natural variability provides context. Implication 2. The Holocene is abnormal. The past 11,700 years have been unusually stable and warm. Perfect conditions for agriculture and civilization. For 90% of the past million years, Earth has been colder than today, much colder, with ice sheets, lower sea levels, different ecosystems. The climate we consider normal is actually abnormal. A brief interglacial pause. This means human civilization developed. During anomalous conditions were adapted, culturally, technologically, economically, to Holocene climate agriculture, infrastructure, settlement patterns, all assume Holocene stability. Natural progression would return Earth to glacial conditions eventually. We're living in a Goldilocks moment between ice ages. Fortunate timing for civilization. Implication 3. Ice ages shaped humanity. Human evolution occurred entirely during the Ice Age, past 2.6 million years. Our ancestors survived repeated glacial-interglacial cycles. This shaped us. Behavioral flexibility, adapt to changing conditions. Social cooperation, coordinate to survive harsh environments. Technological innovation, tools, fire, clothing, shelters. Cognitive sophistication, problem-solving, planning, cultural transmission. We are products of Ice Age evolutionary pressures. The rapid climate changes of the past 100,000 years, DO events, Younger Dryas, likely selected for adaptability. Populations that couldn't adjust to abrupt climate shifts died out. Those that survived passed on genes and cultures emphasizing flexibility and innovation. Modern humans' cognitive abilities might be partly explained by Ice Age survival challenges. Implication 4. Climate change is an existential risk. Both natural and anthropogenic climate change pose existential risks. Natural Ice Age, if it occurred, ice sheets would cover regions where hundreds of millions live: Canada, northern USA, northern Europe. Agricultural disruption, growing seasons shortened, crop zones shifted, conflicts over habitable land and resources, forced migrations. However, natural ice ages are slow, thousands of years, providing time to adapt. Anthropogenic warming, current trajectory, sea level rise, displacing coastal populations, agricultural disruption, crop failures, heat stress, droughts, extreme weather, hurricanes, floods, wildfires, ecosystem collapse, extinctions, coral reef death, forest dieback, conflicts over resources, and anthropogenic warming is rapid, decades to centuries, limiting adaptation time. Both represent civilization-scale challenges. Understanding the 100,000-year cycle shows climate change, natural or human-caused, is one of the major forces shaping human fate. We've survived natural climate changes before, but now we're causing our own climate change at unprecedented rates, adding to natural variability. Implication 5. We've become a geological force. Humans have joined the ranks of geological processes: volcanism, asteroid impacts, orbital variations, capable of causing global climate change. Our emissions have overridden natural cooling trend, delayed next ice age by tens of thousands of years, increased CO2 to levels not seen in millions of years, caused a warming rate unprecedented in geological record, except for asteroid impacts. We've broken out of the 100,000-year cycle, at least temporarily. This is the Anthropocene, a proposed new geological epoch defined by human impact on Earth, system. Future geologists, if any exist, will see a clear boundary in rock record. Sudden increase in CO2, rapid warming mass extinction, radioactive isotopes from nuclear testing, plastics, metals, concrete in sediments, extinction of megafauna. Our impact will be visible in geological record for millions of years. Implication 6. We bear responsibility. Natural ice age cycles are beyond human control. They're driven by orbital mechanics operating on 10,000 to 100,000 year timescales. We can't prevent natural ice ages from eventually occurring, though we've delayed the next one. But current warming is within our control. We caused it through fossil fuel emissions. We can mitigate it through emissions reductions. We can adapt to it through technology and planning. We bear moral responsibility for impacts on future generations and other species. The Ice Age cycle provides perspective. Climate changes naturally, but that doesn't excuse our causing additional rapid change on top of natural cycles. Implication 7. Fragility and resilience. Ice Age cycles demonstrate Earth system resilience. Climate oscillates between glacial and interglacial life survives. Species adapt, migrate, evolve. Ecosystems reorganize but persist. Carbon cycle, water cycle, energy balance find new equilibria. Earth will be fine. Ice ages come and go. Life continues. The planet has survived worse. But individual species and civilizations are fragile. Many species went extinct during ice ages, megafauna extinctions. Human populations crashed to small numbers during glacial periods. Climate change poses existential risk to civilization, though not to humanity as a species. We're remarkably adaptable. Earth endures. Species and civilizations come and go. Our challenge, ensuring our civilization persists through the climate changes we've initiated. Implication 8. Long-term thinking. The 100,000-year cycle requires thinking on timescales far beyond human lifetimes or civilizational memory. Human lifetime, 80 years. Recorded history, 5,000 years. Civilization, 10,000 years. Ice Age cycle, 100,000 years. Our actions today affect climate for tens to hundreds of thousands of years. CO2 emitted today remains in atmosphere for thousands of years. Ice sheet changes triggered today play out over centuries to millennia. Sea level adjustments take thousands of years. Ecosystems take millennia to recover from disruptions. We're making decisions with multi-millennial consequences based on quarterly profit reports and election cycles. Long-term thinking is essential but difficult for species whose individual members live decades and whose civilizations have existed for at most 10,000 years. Implication 9. Knowledge and wisdom. Understanding the 100,000-year cycle required centuries of scientific observation and theory development, ice core drilling and analysis, ocean sediment core collection, astronomical calculations, climate modelling, international cooperation. This knowledge is recent. We've only understood Ice Age cycles for 50 years. This knowledge is precious, allows us to understand our place in Earth's climate system, enables prediction, where we are in cycle, what comes next, informs policy and adaptation, provides perspective on current changes. Preserving and expanding this knowledge is essential for future generations who will live with the climate changes we've initiated. Implication 10. Hope and concern. The Ice Age cycle provides both hope and concern. Hope. Climate has always changed. Change is natural, not catastrophic. Inherently, life adapts. Ecosystems reorganize, species evolve, planet endures. Humans have survived dramatic climate changes before. Glacial interglacial transitions, abrupt changes like Younger Dryas. We have technology and knowledge previous humans lacked. We can potentially manage climate deliberately if necessary. Concern: current warming rate exceeds anything in Ice Age cycles, except possibly asteroid impacts. We're approaching multiple tipping points simultaneously. Consequences play out over thousands to tens of thousands of years, longer than civilizational memory. We're conducting an experiment on Earth's climate system with unpredictable outcomes. The next ice age will eventually come, unless we've permanently disrupted the cycle. What will Earth look like then? The balance. Cautious optimism tempered with recognition of genuine risks and responsibilities. Conclusion: sleeping through cycles. As you drift towards sleep tonight, perhaps you'll dream of ice, vast sheets of ice kilometers thick spreading from the North Pole southward, covering landscapes you know, burying cities that haven't been built yet, advancing slowly but inexorably at walking pace, year after year, century after century, millennium after millennium, until half the northern hemisphere lies beneath white frozen weight, until sea levels drop exposing continental shelves, until Earth transforms into a planet you wouldn't recognize, a planet where humans huddle in refugia near the equator or on ice-free coasts, surviving but changed, waiting for warmth that will eventually return as it always does, as the cycles decree, as the orbits determine, as the feedbacks amplify. Warming following the cooling, ice retreating northward, seas rising, forests advancing, civilizations emerging in the warm intervals between the ice. Perhaps you'll dream of the rhythm, 100,000 years of cycling between ice and warmth, sawtooth pattern of slow cooling and rapid warming, repeating dozens of times across the past million years, pattern as regular as heartbeat on geological timescales, pattern driven by Earth's relationship with the Sun, by the slow wobble of our axis, by the elliptical dance of our orbit, by the tilt that brings seasons, all combining to create the conditions that allow ice to grow or force ice to melt. Orbital mechanics translated into planetary climate through the amplifying mechanisms of ice, albedo feedback and greenhouse gas, changes and ocean circulation shifts, transforming subtle variations in sunlight into massive climate oscillations that define the dominant state of our planet. Perhaps you'll dream of where we are now, 11,700 years into an interglacial, living in the warm period between ice ages, enjoying the stability that enabled agriculture and cities and everything we call civilization, taking for granted that this is normal when actually it's abnormal, a brief respite, a statistical outlier in a planet whose dominant condition for the past million years has been glaciation, approaching the point in the cycle where natural progression would lead back toward ice. Except we've intervened. We've added CO2 and methane and other greenhouse gases, we've warmed the planet rapidly, we've overridden the natural cooling that would have begun the next ice age, we've delayed or prevented the next freeze by tens of thousands of years, we've broken out of the cycle, at least for now. Perhaps you'll dream of the future, uncertain, branching, dependent on choices we make over coming decades about emissions and energy, and how we relate to Earth's climate system. A future where, if we act wisely, the next few centuries see manageable warming and adaptation, or a future where, if we act foolishly, multiple tipping points trigger cascading changes we can't control, but in either case, a future where the next ice age waits in abeyance, delayed by our greenhouse gases, suspended until natural processes slowly remove CO2 from the atmosphere over tens of thousands of years, at which point the orbital cycles will again determine whether ice can grow and Earth will resume its pattern, unless we're still here, still managing climate deliberately, still preventing the ice through technology and intention, having become permanent stewards of Earth's climate rather than temporary disruptors. And perhaps as you dream, you'll understand that we live on an ice age planet, a planet that freezes regularly, a planet where our current warmth is temporary and unusual, a planet where the dominant pattern for 1 million years has been cycling between ice and warmth every 100,000 years, where our entire species evolved during these extreme oscillations, where our cognitive abilities and cultural adaptability were forged in the furnace of abrupt climate changes that killed those who couldn't adjust and favoured those who could innovate and cooperate and transmit knowledge across generations, where we are products of ice age pressures, survivors of climate changes that would have destroyed us if we weren't so remarkably flexible and inventive and stubborn. And perhaps you'll wake tomorrow with new perspective on climate, understanding that change is natural but our current changes are not, that cycles exist but we've disrupted them, That Earth will eventually return to Ice Age patterns, but we've delayed them. That the climate stability we've enjoyed for 11,700 years is precious and temporary. That every generation of humans before us lived with climate instability, but we're the first generation with both the knowledge to understand the cycles and the power to disrupt them, giving us both unprecedented responsibility and unprecedented opportunity to shape Earth's climate future for thousands of years to come. Sleep well, dreaming of ice ages and interglacials, of orbital mechanics and feedback loops, of ice sheets advancing and retreating across deep time, of the 100,000-year rhythm that has defined our planet's recent climate and shaped our species' evolution, of where we stand in that cycle, near the end of an interglacial, approaching the point where ice should return but probably won't because we've changed the rules. We've added enough greenhouse gases to override the orbital forcing that would initiate glaciation. We've become a geological force, rivaling volcanism and asteroid impacts in our ability to change global climate, making us responsible for managing the consequences of our power. The ice will return eventually, in 50,000 years, in 100,000 years, in 200,000 years, whenever CO2 returns to lower levels and orbital configurations again favour ice sheet growth. Unless we've fundamentally altered Earth's climate system in ways that prevent ice ages permanently, which is possible but unlikely, or unless human civilization or its successors manage climate deliberately for millions of years, actively preventing ice ages through continued greenhouse gas emissions or other technologies, which is conceivable for a sufficiently advanced civilization. But for now, in the present, we face not the cold of ice ages but the heat of our own making, not the slow advance of glaciers but the rapid retreat of ice sheets in Greenland and Antarctica, not sea level drop but sea level rise, not gradual cooling over thousands of years but rapid warming over decades, not the natural progression toward the next ice age, but our disruption of that progression and our uncertainty about what we've done and where we're heading. Rest well. Tomorrow the work continues, the work of understanding Earth's climate system, of measuring the changes we're causing, of developing technologies and policies to manage those changes, of adapting to the warming we've already caused and the additional warming we've committed to, of making choices that will determine climate for thousands of years, of bearing the responsibility that comes with being the first species on Earth powerful enough to override the natural climate cycles that have dominated for millions of years. Good night, inhabitant of an interglacial period on an Ice Age planet. Good night, product of 1,000,000 years of Ice Age evolution. Good night, member of the first generation to understand why Earth freezes every 100,000 years and the first generation to prevent it from freezing. The cycles continue, modified by us but not eliminated, delayed but not stopped, overridden for now but waiting in the deep future, ready to resume when conditions allow, when CO2 declines, when orbital configurations favour ice, when feedback mechanisms amplify cooling into glaciation, when Earth returns to its dominant state of the past 1,000,000 years. Ice Age. We live between the ice, in a warm moment between frozen epochs, in a stable period within an unstable system, in an interglacial that has lasted 11,700 years, and would naturally end within a few thousand more, except we've intervened, we've changed the timeline, we've become part of the cycle rather than passive observers of it. Sleep well. Dream of ice ages past and ice ages prevented. Dream of orbital cycles and feedback mechanisms. Dream of the 100,000-year rhythm and our disruption of it. Dream of where we are in deep time and where we're heading, and wake tomorrow ready to face the climate challenges of our moment. Not the distant future ice age we've delayed, but the immediate present warming we've caused and the responsibility we bear for both.